So we have learned how machines store numbers in binary format. And we also learn hexadecimal numbers, which is a neat way to represent binary numbers, right? Because it doesn't the string is a lot shorter, right? And it makes debugging and programming a little bit easier. So now the question is, how are characters stored? At the end of the day, everything that's stored in the computer are zeros and ones. So it's a matter of what's the schemes that we use to store characters, right? If a variable is a number, then we know how to interpret it, right? And by looking at the zeros and ones, the binary numbers, and we can convert that to decimal, right? So that human can understand. If that variable's type is a character, then the zeros and ones would mean something different, right? We would use some sort of a binary number to map scheme to map to a whole character set. Okay. Now, information technology was mostly invented in the United States and some in UK. So it's mostly in the English-speaking world. And in the early days, we were only concerned about representing English characters. Okay, so the first standard that came out, it's by the American National Standards Institution. I think it's the predecessor of that, came out with the ASCII, ASCII standard. Basically, it defines what binary numbers would map to what character, would represent what characters. Okay, at the time that the first standard that's defined is called ASCII, also known as ASCII. ASCII stand for, I think, American Standard Code for Information Interchange. It basically uses 0 to 127. And now, when you recall, 0 to 127, that's 7 bits, right? And we know that the smallest unit that we use in computer generally is a byte, a bit, right? So it leaves an extra bit, the most significant bit, unused when we map ASCII numbers to the characters, right? So the original thinking is that we're going to map the English keyboard to, we will define code to represent the entire English keyboard. Okay? Now, because there's an extra bit, right, in the byte there, so many vendors would come up with their own mapping beyond 127. Right? From 0 to 127 is defined as ASCII standard, and then beyond 127, from 128 to 55, it would be defined by the vendor, such as early days in IBM. They will define their own mapping beyond the 127. And now later on, there is a ANSI, American National Standard Institution, came up with the full 8-bit, right, the entire byte from 0 to 55 mapping of characters. So that is also known as ANSI. For the ANSI mapping standard, the first 128 characters are the same as the standard ASCII. And then as computer technology proliferate throughout the world, right? And first you need to support other European languages, French, right, Norwegians, etc., with accents and Spanish, right, and all that. So the ASCII or ANSI standard are just insufficient, right? So the ANSI standard committee came up with a new standard called Unicode. Unicode can represent over 65,000 characters. Okay, that would be enough, pretty much, to support all languages in the world, right? And one could argue 65,000 may not be enough to include all the Chinese characters, but you are talking about very, very rarely used characters beyond 5, 6, 7,000. And so that's Unicode. Let me go to the... So here is a ASCII table. And when you run Windows in console mode, this is the code that Windows uses. Well, Windows in general uses ANSI, but the first 128 character ANSI and ASCII are the same. So the way to read this is that you could have on the top, there's a number in decimal in the bottom. Let's see, the first row is decimal, and the first column from the left is also represent decimal. Okay, so the more interesting thing is not the decimal representation, it's more of the hexadecimal. And you will come to appreciate why hexadecimal is used more widely than decimal in computer, because it's just really, really simple. Okay. So the number here, from 0 to 7, okay, it represents the bit from, let's see, from the right to left. Let me just draw a picture here. Okay, so we are talking about using 8 bits, right? In fact, just 7 bits, okay? As defined in the ASCII standard, you only use 7 bits. And this bit is up to vendors, whatever vendors use. So in the table you see here on the hexadecimal, here's from 0 to F. That represents the lower, less least significant digit, it represents this part of this 4-bit, right? So it's from 0 to 1, 1, 1, 1, which is, it represent 15. Okay, that's the number 15. So 0 to 15. All right. And then on the higher hexadecimal, we are only using 3 bits. Okay. So it would be from 0, 0, 0 to 1, 1, 1. Now 1, 1, 1 is 7. So now you come back here, look at it. This line represents the more significant hexadecimal digit. This is represent the less significant hexadecimal digits, right? Here from 0 to 15, here's from 0 to 7, okay? So if we look at the letter A, letter A is represented by the hexadecimal number 4, 1. So it would represent 4, 1, so it would be 4 is 1, 0, 0, 1 is 0, 0, 0, 1. Okay, so this binary number represent the letter A, capital A. So that's how you read this table, this mapping table. Okay. Now for decimal, it's not as simple to do the straight mapping. So for decimal, it would be 64 plus 1, right? It would be 65. And if you convert the hexadecimal number 41 to decimal, you'll get 65. But let's focus on hexadecimal, right? You don't have to do the addition. You basically just look up this table. Let's say X. X would be 5, 8. And let's see, Z would be 5, A. Okay. And this is the beyond 127, right? So it starts from 8 to F. Now we are using the extra bit here. So the second table, we are talking about you start from 1, oops. Start from 1, right? Like 1, 0, 0, 0, 0, 0, 0, 0. And for the least significant digit, it will go all the way to 1, 1, 1, 1, which is 15, right? F. In here, you start from 1, 0, 0, 0, which is 8. Okay? And all the way to 1, 1, 1, 1, which is F. So with the first table and the second table, we have the entire 256 possible combination using a 1 byte or 8-bit representation. Okay, so this is part of the ANSI standard. It's not part of ASCII, but if you look at here, this page is both ASCII and ANSI standard. Okay, just quickly talk about Unicode. Unicode, like I said earlier, can represent over 65,000 characters and symbols, etc. There are several schemes, and we're not going to go into great details of that. UTF-8 is used in HTML. UTF-8 could have between 1 to 4 bytes. Most characters are represented by 1 byte, but some of them, when necessary, like when it comes to a foreign language, like a Korean, Japanese characters, and it's going to use more than a 1 byte. But it's variable, and it's either 1 or 2 or 3 or 4. Okay. And then there's another scheme called UTF-16 encoding, which is it uses 2 bytes or 4 bytes to map, characters. And then UTF-32 uses a fixed length of 4 bytes. Okay, so UTF-8 is more efficient, right? Because when it's not necessary to use, in terms of space, when it's not necessary to use multiple bytes, it will use single bytes. When it needs only 2 bytes, it will only use 2 bytes. And then UTF-32 is not as space efficient, and you can use that in scenarios where memory storage space is not a big concern, but processing speed is. Then the UTF-32 is faster than UTF-8. UTF-16 is sort of a compromise between the two, right? UTF-8 and UTF-32. And I believe in Windows, when you save a file, a text file these days, the default is UTF-8. Now terminated string, and as we learn from C string, not C++ string. C++ string is a object type. I'm talking about the array of characters that's represented by C programming languages. A string is usually terminated by a null byte. A null byte basically is all the bits in that byte are 0. So if you look at the null character here, it's 0. So the lower one, here's the more significant, right? Digit in hexadecimal is 0, and the lower digit is also 0. So the null terminated strings and usually is an array of characters with the last character being a null byte, and that signifies the end of the string. Okay, so the numeric code for the string ABC123, as I've shown you earlier, it would be 41H, 42H, 43H, etc. Right? And the ASCII table is included in the back cover of the textbook. So numeric data representation. So this is something that you have to make a distinction of when you're looking at numbers. Let's say a decimal number 65. How is 65 displayed? Well, it depends how you treat it, right? If you treat 65 as a number, then it is stored internally, right, as a the binary number 01, 000, 001. Okay, that would be the number 65. That's pure binary. However, if you want to represent the decimal number 65 in a string of binary digits, you're going to display them as characters in 0 or 1 characters. Then it will take 8 bytes. So internally, 65 can be represented by 1 byte, right? But to display 8 characters representing the string of digits in binary, then it takes 8 characters, which is 8 bytes. Okay. Now 65 can also be represented as the character 6 and character 5, right? As a string that has 2 characters, 6, 5. Then it takes 2 bytes. Now, if that is stored as hexadecimal number, then you are talking about using actually 1 byte, right? With the lower 4 bits as 0001, and the upper 4 bits will be 0100. That represents hexadecimal number, not character, for 1. However, if you're representing them as ASCII hexadecimal, then you will need 2 bytes, right? 1 byte to represent the character 4, the second byte represent character 1. Okay? Now, if you assign this decimal number to a variable that's declared as a character, and then when you display that, the content of that is not going to display number 65 because you declare that variable as a character. So it's going to use the ASCII mapping, and it's going to map 65 to the capital letter A. Okay. So you can try it out using your C++, using the IDE, and then try this 2 lines of code. And, X is declared as an integer, right? It got assigned the number 65. However, right before you send it to output, so if you just say X, right, it's going to display 65 as numbers, as, 2 characters as numbers. However, if you cast the X to the type character before you send it to output, then it's going to treat this X differently. It's going to display the letter A, which is the number 65 represents in ASCII code. We are going to talk about Boolean operations next.